In this video, I'm going to walk you through how to use the ADC of the JA module. Last time we looked at the DAC, so we were creating a voltage output. Now we're going to read a voltage in. And I'm just going to show you the setup initially and how to get some values. And we're going to look at the integer value in units of ADUs. That's the analog to digital units directly from the ADC. And then we're going to convert that into a voltage. And that's all we're going to do in this video. Of course, I need a voltage to measure in the ADC, and I'm going to use the output voltage of the DAC. And so to do that, I'm just going to grab a short wire. I need to connect those two pins together. So I'm going to get a short wire. Doesn't have to be very long. And again, we want to get in the habit of making these wires as we need them, custom wires, because we're going to be doing this over and over again. And there we go. There's my wire. I'm going to use it to short out the adjacent pins in the JA module that'll connect the DAC and the ADC. And so here we go. It's these two pins here, and we're done. And we're still monitoring the output voltage from that DAC, and now it's the input voltage to the ADC. We've got something to measure, and now let's set up the code. And then to do that, it's really simple. We set up the resolution for the DAC with the analog write. We're going to do the same thing for an analog read. So I'm going to just copy that line. We'll paste it in here, and that's going to be an analog read, and the resolution is 12 bits. That means the number is going to go from 0 to 1095. Before I read a value, I want to assign it to a variable. And so I'm going to introduce two more variables. These are going to be associated with the ADC. And in the same way that I'm going to have a value I get directly from the ADC that is in units of ADU, 0 to 1024, an integer, I'm going to save that as one variable, and then I'm also going to get another variable where I convert it into voltage. And I'm just going to do that in order to illustrate and so we can see those two numbers. So the first variable is going to be along, and this is going to be the voltage from the ADC channel 1 in units of ADU. And so you can see how convenient the labeling scheme, the naming scheme I use for variables. And then the next one is going to be a float version of a voltage from the ADC channel 1, and this is going to be units of volts. So I've got my variables, and now we're going to come along here and we're going to read a value from the ADC. So that's going to be an analog read. Oops, helps when you spell it correctly. Analog read. It's from channel 1, and that's it. That command says, okay, go read that value and return it. And this is a number now in units of ADU. I'm going to assign that to one of the variables. So this is going to be the voltage from channel ADC1 in units of ADU. And that equals the analog read. So now I've got a value from the ADC in this variable, and lastly I want to convert that variable into volts. So now the variable that is going to store the ADC in channel 1 information in volts, well, how do I do that conversion? The whole range is 0 to 495, and so if I look at the values in ADUs, and I look at the values in volts, I'm going to start at 0 to 495. 40, this is 4095 is the range, and the voltage level is going to be 0 to 3.3 volts, which is really, it's not quite 3.3 volts. It's whatever that reference voltage I measure. And so I'm going to use the same value that we used for the DAC. That's going to be the upper limit. And how do I do this scaling? It's really simple. I find out, for a given value here, what fraction of the way is it up here, and that's the same fraction of the way it is up here. And so to convert the value in ADUs into the value in volts is just taking that fraction and multiplying by the full value over here. And so this is going to be the value in ADUs the voltage from the ADC channel 1 in ADUs divided by the 4095. That's the full value. That's the fraction, how far to full scale I am. And I want to do that as a floating point calculation. And so I'm going to divide that by 4095.0. That forces a floating point calculation. That's the fraction. And then I want to multiply that by my full scale range, and I'm going to use the DAC reference voltage. So it's the voltage on the DAC, the reference in volts. And there we go. Now I could use just 3.3 volts, but we know it's not exactly that. It's a little bit less. And hey, it's free to get a little bit more accuracy, and we'll check the accuracy level. Okay, so I have the two values, and now I want to print them out. We're going to print them to the serial monitor. And to do that, I'm going to use a print statement. It's a serial.print. And let's see. It's going to be, I'll plot the ADU value first. So it's the voltage on the DAC channel 1 in ADU. And then I want to print a tab character. So I'm going to do on the same line, serial.print. And the tab character, it's that funny, it's a backward slash T. That's a tab. And then the next line is going to be the value from the ADC in volts. So it'll be serial.print in the voltage from the ADC channel 1 in volts. Now, normally I'll print out a floating point number with 2 decimal places. So that's within 10 millis. I really want to get 3 decimal places because I want to be able to see the millivolt value. I could do 4 decimal places as well, but for now we'll do for 3. So I'm going to add a 3 here to say 3 decimal places. It's not the default, which is 2. And there we're done. Now, because I'm printing out on the serial port, I need to tell the JAW module set up the serial monitor. Or set up the serial link. So in the setup, I need a serial.begin line that will set the baud rate for the USB cable. Now, the default is 9600. Yeah, you can use 9600, but if you can get away with a faster rate, why not? It's free. And I have found generally that using 2 million as the baud rate is a pretty safe, robust value. So I'm going to put 2 million as the baud rate. And so now we've set it up, we're ready to go, we're ready to print out a serial monitor. Now, just to clean things up, I like going to Tools, Auto Format. Just makes it a little easier to read. So we define the variables, got our 2 new variables. We're going to set the resolution, we're going to set the serial link, and now we're going to turn on the DAC, set the voltage, roughly that 2 volt value. We're going to read the value on the ADC. We're going to convert it to units of voltage by scaling it, and then we're going to print out the integer value, and we're going to print out the DC voltage. Okay, and the other thing that we're going to do is we're going to look at that voltage with our digital multimeter. And we're ready to go. Let's upload the sketch. So we upload, let's see, it's compiling, uploading, and it just reset the DAC, turn it back on. There's our value, and now if we look at the serial monitor, we ought to see these 2 values coming out, and we should see something that 2 volts is 2/3 of the way, so maybe in the 2000, 3000 ADU value, and we ought to see something close to 1.99 volts. So let's turn on the serial monitor. Now, one thing, so here's a good example of debugging. So hey, the numbers are coming out, but they're coming out horizontally. And well, that's because I forgot to put a line feed over here. So add the line feed, and that will put this on add a line feed after this, so that every combination of the 2 numbers will be on a separate line. So now let's upload this data. Now, I was running the serial monitor, right? I'm uploading. It was able to turn off the serial monitor, finished uploading, and now if I go back to the serial monitor, I ought to see my two columns. And sure enough, here they are. So the first column is the value in ADU, and sure enough, hey, look, there it is, between 2000 and 3000. The second column is the voltage, and I'm measuring 1.98 volts roughly. And there's a little bit of change here in the last column. Now, what is the actual voltage? 1.99. So I am less than 10 millivolts off. And at 10 millivolts, that is 0.5%. And so just out of the box, absolute accuracy is within 0.5%. Now, it would be nice, I got this data come out really fast, it'd be nice to average some of this, average some number of points. And so let's do that just really quickly, and then we will display the average value. And so let's write the code that will do some averaging for us. So I'm going to turn off the serial monitor here, and now let's write a little code to do the averaging. In other videos, I'll show you how we can average for an integral number of power line cycles, which is a better way of doing averaging. But for now, we're just going to take 1,000 points. And I'm also going to be a little lazy about it, and I'm going to use this variable that I already have to store the consecutive sum of each consecutive measurement in ADUs. It's long, so we can store a lot of values. And we'll store that, and then we'll do the conversion from the total number. We'll divide it by the number that we're averaging when we convert it into volts. And so to do that, I have to initialize that variable to be 0 so that we start out counting from scratch. So I'm going to have that voltage of the ADC channel 1 in ADUs equal to 0, the first line. And now I'm going to use, and it's ADC, not DAC. And I'm going to use a for loop. And the format for a for loop, the syntax is for, let's see, I'm going to use something really clever. I'm going to use an index value of I equals 1 until I is, well, it's still less than or equal to 1,000. And then I'm going to increment it by 1. And so there's the for loop. Now, if you forget, oh, what's the syntax for this? If you click the mouse in the command or the statement and you right mouse click, you get a contextual menu. You get a find in reference. It'll pull up the reference page for the for statement, and you can check the syntax. Yep, it's for small case. We define or declare the variable. Here's the starting value. Here's the test. As long as it's less than, or as long as this statement here is true, it'll iterate through the loop. And then here's the increment value, and there it is. So it's exactly the way we have it set up. And in this loop, I'm going to take this value here. I'm going to read this value, and I'm going to add to it the previous value. So this is the voltage from the ADC channel 1 in ADU. Simple as that, except that I need a plus sign here. There we go. So I'm going to take the voltage I get from the ADC, I'm going to add it to the previous value, and I'm just going to keep on doing that over and over. And so this is going to get bigger and bigger and bigger until I'm done with 1,000 averages. And now the output of this is 1,000 averages. And so I'm going to convert that into the voltage, but I have to divide this by 1,000. Now I don't want to use an integer, otherwise I lose all those significant digits that I've accumulated here. They'll just get factored out and cut off. And so I want to convert it to a floating point, and that's where I have the divide by a floating point number. So this is now the average ADU value as a fraction of the full scale. So I scale it to the full scale, and then I scale it to voltage. And now I'm done. And I've taken out the other terms because I don't care about the ADC, about the ADU values. I just care about the voltage. Now, one last thing I like to do is do auto format just to check on things. It cleans things up a little bit. Okay, and now we're ready to go. So let's upload. We're compiling, uploading. And now let's take a look at our serial monitor. And here's the serial monitor. And look, those values are really stable, and we're getting 1.986. Now let's see what our voltmeter is reading. Our voltmeter is reading 1.991. And so what's the difference there? So we're a difference of about, let's see, 4 in the last digit. So that's 4 millivolts. So our absolute accuracy of the ADC is about 4 millivolts out of 2 volts. That's less than 0.2%. So you can see the absolute accuracy of the ADC using this little trick of scaling it with the voltage on the 3.3 volt rail that we actually measure. You can see that's giving us better than 0.5% absolute accuracy. That's what we want. Okay, and now we're ready to go to the next step.